Artificial intelligence is moving off the screen and into the real world. Currently, robotic systems rely on fragmented pipelines. An agent needs one model to process visual inputs, another to interpret language, and a third distinct policy model to execute physical movement. Moving data across these boundaries creates latency. Lost time leads to compounding spatial errors, causing robots to hesitate or miss their targets during physical tasks. Nvidia's Cosmos3 research dismantles these silos. The project involves more than 293 contributing authors, signaling a massive industry-wide effort to solve the problem of embodied intelligence. Cosmos3 is an omnimodal world model. It processes language, images, video, audio, and physical action sequences within a single continuous space. By unifying these disparate modalities, Cosmos3 serves as a native brain for robotic agents, removing the data bottlenecks that previously led to execution failures. To understand this framework, look at standard multimodality. Structurally, it functions like an assembly of delegates who speak different languages. In typical networks, vision and language models are isolated. Data must pause at a translation layer to communicate. For robots processing high-frequency video and physical actions, this bottleneck causes delays, making real-time coordination difficult. Omnimodality removes the need for translation. It uses a single processing core that interprets all data types natively. Cosmos3 takes heterogeneous data, from discrete text to dense video, and processes it within the same latent space. Within this model, a physical action sequence is simply another data type, treated no differently than a pixel or a word. Eliminating the translation overhead provides the mathematical efficiency needed for robotic agents to react to their environment instantly. This is made possible by a mixture of transformers architecture. Usually, forcing discrete text logic and continuous robotic motion into one network causes interference, which lowers performance for both tasks. Cosmos3 avoids this conflict by acting as an intelligent sorting facility. Instead of a single monolithic processor, a router directs different data types to specialized processing nodes, called experts. Text prompts flow to language-optimized blocks, while video bypasses them, routing directly to spatial temporal nodes. Continuous physical action sequences are tokenized to be processed by this same routing logic. The activated expert blocks now converge back into a single output stream, producing a continuous waveline representing a robotic action vector. This shared routing system allows Cosmos3 to map semantic intent directly to physical torque, bridging the gap between reasoning and motion. Architecture alone is not enough. The model requires the correct data to understand the physical world. Just as a pilot uses a flight simulator, a robotic AI needs a world simulator to learn how reality works. Standard internet videos do not provide enough information to teach a model about mass, friction, or the strict physical constraints required for robotic manipulation. To solve this, Nvidia trained Cosmos3 on massive, curated synthetic datasets. Generating environments procedurally exposes the model to millions of physical edge cases. These scenarios would be impossible to capture with real robots. These datasets explicitly encode object permanence and mass dynamics into the training process. These synthetic simulators allow Cosmos3 to understand the physics of reality rather than just mimicking the visual appearance of a video. Bringing the architecture and data together requires a joint processing pipeline. Training poses a mathematical conflict. Predicting text tokens is a discrete, step-like process, while generating robotic actions requires a smooth, continuous gradient. The pipeline balances these competing objectives, so neither modality dominates the model's development. This balance is maintained during inference, when the model is actively controlling a robot. The system ingests real-time sensor data and provides high-frequency control signals without losing its reasoning capabilities. Reconciling these two disparate mathematical objectives is what allows a generative model to function as an active physical agent. We can verify this performance by looking at how Cosmos3 compares to specialized, single-purpose models. In purely generative tasks, artificial analysis ranks Cosmos3 as the best open-source text-to-image and image-to-video model available. It also leads in physical policy tasks, achieving the top ranking on the RoboArena benchmark. A single generalist system has outperformed models designed specifically for individual domains. To support wider research, Nvidia has released the code, checkpoints, and synthetic datasets to the public. The release is governed by the Open MDW-1.1 license from the Linux Foundation. Providing open access to a state-of-the-art omnimodal model prevents physical AI from remaining locked behind proprietary APIs and accelerates global robotics development. There are limitations to consider. Training and running an omnimodal mixture of transformers requires massive amounts of compute power. Additionally, the model still faces challenges with compounding errors during very long, complex physical tasks. To wrap up, these are the 3 core takeaways from the Cosmos3 research. First, Cosmos3 unifies text, video, and action into a single framework. Second, its specialized architecture and synthetic training give it a native understanding of physical laws. Cosmos3 provides the foundational software needed for the physical agents of the coming decade.